Jnanam paramam dhyayam. Knowledge is supreme.
So, next we want to prove the rank is M. So, to prove that I will consider the last, so we have this matrix now dFi by dxj's, and we are reading this mod P, this matrix, and we want to decide what is the rank. So, now, so first of all, this is a matrix. I will take this as how many the columns are more. J is the column index and I is the row index, and there are how many FIs? There are M FIs. So, there are M rows and more columns actually. So, I have to choose the columns to show that the rank is M. I choose now the last M columns. So, choose last M columns. That means which variable involves there. So, we have to differentiate with respect to which variables. That means x k plus 1 to x k plus m. These are the variables we need to differentiate. And now I want to claim that this is actually a lower triangular matrix with diagonal entries. So, this last columns. So, the matrix now is M cross M matrix. Let us write it so that it will be easier to understand. It starts with F1, then starts with dx k plus 1 and goes to df1 dx k plus m, which is of course m. This is the first row. The second row is df2 dx k plus 1 df2 dx k plus 2 and so on, df2 dx k plus m and so on. This one is df m differentiating with dx k plus m, and this is df m dx k plus 1. This is that matrix. I claim this is lower triangular. So, that means this, first of all, the diagonal entries are not in P, that we have chosen, right, because we have chosen the third claim in the separability case. The third claim we have chosen this and that means this. These are the diagonal entries. So, the diagonal entries are not there. So, what are the earlier entries? For example, this one. Yes, see, actually they are in the kernels. So, when you different this variable does not appear there. So, they are actually lower triangular. So, therefore, the rank is correct. So, all this happened in this lemma. It is not a magic, it all happened because of the following reason. This ring, if you take polynomial ring in any number of variables and localize at some prime ideal P, this ring is regular, this is regular local. Because you see, this is of dimension how much? Height P. Height P was M, and there we found F1 to Fm, so that locally P is generated and height is M. So, therefore, F1, F2, Fm must be the minimal number of generators for the prime maximal ideal in the local ring. So, by definition this ring is therefore regular. So, all this happened because this ring is regular, and this one wants to abstractize this. That is the ultimate generalization of this, and also ultimately I want to get rid of these coordinates. So, that also okay. So, this was one lemma which we need. The other lemma is the following. So, this was the lemma 2, and then we will patch up. So, lemma 2, and all these calculation will also become much neater if you make some definition abstract. So, for example, there is a concept of scalar differentials. If you go to modules and if you learn the scalar differential modules and their universal properties, then all these coordinates and all this will go away, but at the cost of some abstracting. Okay, that I will come up after when we have enough room for playing. Okay. So, what is the lemma 2 I want? Lemma 2 is, suppose I have now ideal in a polynomial ring in n variables and the generator of that. So, suppose I have an ideal A which is generated by m polynomials f1 to fm in the polynomial ring in n variables in k x1 to xn. And of course, k is the field, and suppose we have a prime ideal P. P is the let us call this as A again. Suppose I have a prime ideal P in A which contain this A. And again I am putting L to be the, you take first of all the A by P and the quotient field. This is same thing as you take the localization first and take the residue field. It is this. So, whether you take the localization first and then take the residue field, or take the residue ring and then take the quotient field, these two concepts are same. Okay, then, so in under this situation, what do you want to prove? That rank of the Jacobian matrix, rank of, again I will form the Jacobian matrix. So, dFi dxj mod p. This rank is smaller equal to you take the ideal. So, in a local ring now, take the ideal and take p square divided by p square, and this you are taking in a local ring. I will explain you how it comes from. See this, see you want to, we have this local ring P AP is the maximal ideal. So, you want to test. So, when you want to test, for example, what is the dimension of in a hold on this for a moment. Suppose we have a local ring A localized at M, AM is a local ring. If it is local, then one always want to compute this M by M square and the dimension of that as a k vector space. This is embedding dimension. You always want to compare embedding dimension with the dimension to test regularity. So, if I want to test A by the German A ideal, then I have to localize and take. So, I will have to take A by when I localize it AP, This is a local ring with PAP as a maximal ideal. But in this A, P square may not be contained. So, when I want to go mod, for example, here also if I have an ideal A here and I want to check mod M square may not be contained in A. So, I have to add up that to the in the numerator and then take the quotient. That is why this P square comes. So, that is the reason one. Another reason now it may be better appreciated if I will recall you the notation I was saying. So, this for example, this matrix reading mod P and taking the rank. So, this also will be better understood from this notation. See, for example, I was telling you some time back that if I have a spec here and a prime ideal P here, on the and we are considering the topology on this. So, psychologically one feels better to write a notation X for a topological space. Similarly, for a point small x, right. So, this small x will correspond to this P and this correspond to this, right. Okay. So, this imagine this is a topological side, this is algebraic side. Now, from P what can you do? You can go mod, that is a quotient, that is the residue class ring A by P. A by P is an integral domain. So, therefore, the quotient field is this. This is what we are considering here. So, when you go from A to A by P, you are reading mod P and then considering it as an element in the field. That is how these matrices are done. First you differentiate, read mod P and consider it as a matrix over the quotient field. So, we are considering these maps. So, given any element F here, we are reading it here F mod and then quotient field here. So, this because this corresponds to this x. So, let us write x here just to remember this is a transition from one subject to the other subject. So, this in algebra we denote f bar, right, but one may, this is only a notation. So, I may write it f of x, this is only a notation and then this goes also to f of x because this is infusion map. So, the notation is I want to propose that this map is denoted by like f of x. So, f of x is 0. What should it mean? This should mean this is equivalent to saying that this f bar is 0, but f bar 0 means f is in P. So, this gets translated like that. So, this is very useful. So, therefore, this matrix is like evaluation and then you are doing this thing. This is precisely what you do when you have a finite type algebras. You evaluate at the points in K, then you a polynomial, you evaluate at f of a1 to an. That is exactly saying read this polynomial f mod the ideal maximal ideal corresponding to the point a1 to an. So, then it becomes neater and also less confusing, it is clear that what we are doing. So, similarly, if you translate now this V of the ideal A, this will get translated to what? These are the ideal P's, but then if you translate it, it is P, this is x, this is small x, right, and when does it belong? How do you test this belongs here? When P contains A is contained in P. This is the definition of this, right? And how do you test it? That means every polynomial, I say it polynomial, but it is a ring, right? So, every f belongs to P, and when then f belong to P? When f of x is 0. So, it is the same feeling as like maximal ideals. So, that becomes better and better conceptually. All right. So, we want to prove now the rank of this matrix is bounded by this. So, what this is a vector space now. So, I have to write a dimension here, dimension of L. That is why we have to go mod P square. We want a vector space that means P should annihilate it. So, this and the equal, so if the extension is separable, then the equality will hold here. So, the continuation of this lemma statement. So, the last part of the lemma is, if L over K is separable, then equality holds in A. So, that means the rank is equal to the dimension. So, proof. So, first of all, we have to know how many cross how many matrix is this. This is M cross N matrix, right? These are M polynomials and N variables. So, this matrix D Fi Dxj mod P. So, let me write it of P, that means reading mod P. So, this is actually a matrix in M cross N matrix with entries in a field L. So, this is in M, N, L. L is the quotient field of A by P. And we want to check some inequality about vector space dimension. See, rank of a matrix is equal to the dimension of the image space, and matrix you should think it is a linear map from where to where. If I have M cross N matrix, what do you think it is a map from where to where? The images are the columns. So, images go in M, right. So, therefore, this if you want to think as a linear map, it should be from where to where? Lm to Ln to Lm, right. And you want to prove the rank means the dimension of the image space is less equal to somebody else, less equal to some dimension. Okay. So, and that vector space is what? That is P. So, we have a polynomial ring and localized at P, A localized at P, and the maximality is PAP, and then mod P square AP. This is a vector space of how much dimension? This is A by P, right, A by P and then localize. But A by P has dimension how much? Whatever, okay. So, right now we are not bothered. So, I am going to construct two linear maps. One is from L M to this P by P square and localize at P, that is one, and the other is from here to Ln. This is this is this. I want to construct two linear maps. Okay. What are the linear maps? Okay, the first one first, this one. So, you take any tuple G1 to Gm, and just read them in this. You see, they are polynomials where they are see this, just now I said no, the L is quotient field of A by P, or which is also a residue field of A localized at P. So, each one of them is a polynomial here, right. So, each one of them, so I just want to read them. So, you take this guy, think of these guys as the residues here in a local ring, and now where do you read them? Map it to, you want somebody here. So, this P is generated by F1 to F, A is generated by F1 to Fm, Okay, so look at G, J, F, J, look at this linear combination and read this mod p square, this mod p a p square. This is what is the denominator you want, right? See, what do you want? You want somebody mod this, right? P in a local ring, mod maximal ideal square. That is what you want. So, you have this given this, just multiply by the G I F J, F1 to Fm are given to you. That is generates ideal which is contained in P. So, therefore, all these guys are in P. This element, this sum is in P. So, it is indeed in the numerator, and I want to read mod the square of that. So, it makes sense. Okay, so this is clearly linear map, L linear map, and I want to check its image. What is the image of this map? Image of phi. I say obviously image of phi is this image of phi is contained in this ideal generated by F1 to Fm. So, that means image of phi is precisely, if I take ideal A, add it to p square, mod p square and localize at p. This is the image. That is clear, because we are reading mod p square, p square, and this one not only here, it is actually here in ideal A. Therefore, this is indeed this one. Now, for the other one, for defining C, to define C, I want to define, actually I want to define now P mod P square, localize at P to ln. This I want to define, right? This is what I was looking for, this C. Okay, so suppose I take F in P square, it should go to 0 here, right? If I have to define, this has to go to 0 there. Okay. So, what does this mean? It's in P square means this F we should look like square of somebody, right? So, it should belong to, so that means I need somebody not in P and some guys are in P square. So, that means I need G, Gj, Hj are in P and some H which is not in P and Hf should be like this sum. See, suppose I have such equation, what will it mean when I read in a localization? That means this H go down, and if Gj, Hj's are in P, therefore this part is in the square. So, that is what one wants. Okay. So, suppose I have such an equation with this Gj, Hj is in P and H not in P, and if I differentiate, what do I get? So, that means I will get chain rule. So, H df by dx I plus f dh dxi equal to summation, this summation is over j, summation over j, let us say j equal to 1 to r, gj dhj xi plus hj dgj dxi, such a thing I will get. And where will be this is in any case it will be in P always, because G is in P and H is in P. So, this side is always in P. So, this is in P. So, does not that mean that now when I read, if I have to read mod P square, that means this term will go. So, that will mean that, and this will become 0, this will become in PAP. So, when you read, now read in PAP mod P square AP, in this is m by m square in a local ring. So, I want to read this equation here. So, what do I get? This will mean that df by dxi, this will be in PAP, and this will allow us to define this map. So, what is the map now? Take any f and map it to, of course, when you say f in image here, f mod p, this one is map it to df by dxi and read this mod PAP. This f dxn, and this we are reading PAP. So, you get an element in ln, and so now this map, see, I calculated it here and showed you. I could have directly tell you this map, but that is not. So, one check that this map is L linear. So, this is L linear, and therefore, how do we tie up with our problem? Our problem is now, therefore, I compose. So, psi compose phi. Remember, phi was from L power n, L power m. This is from L power m and to L power n. And now, the Jacobian matrix is precise. So, what we need to prove is the rank is therefore. So, this map is precisely the Jacobian matrix map, and therefore, we want to compute the rank of a composite. So, rank of psi compose phi, this will be less equal to rank of the image of the first one, less equal to. This is clear, because this is a think of this as a linear map from the vector space image. So, this is clear, and this one now you check, it is the rank what we want. This one is the number on RHS, and this is what the number we were looking for. So, if you want to prove equality here, all that you have to prove is that this image is everybody, not image. If you want to prove equality here, then you want to prove that, what will you need to prove? That the rank is m, the rank of this is m, and that was again under the separability assumption. So, earlier lemma also. So, just this will tie up.